and welcome to our second instance of the adventure series that is trying to get a sub-D geometry into Revit with a certain amount of detailization. In this video, we're going to cover the structure, how I would tackle getting let's say, a steel structure from this kind of shape inside of Revit, and also how we can accentuate or enrich the cladding of such structure in a more precise way. So the first video, if you haven't seen it, the first video just had some kind of cladding stapled together and just me showing how you can transfer this type of geometry directly from Rhino into Revit by the use of Rhino.Inside.Revit, and this instance is going to be a little bit more what you would kind of see in the industry. By no means will we be coming even close to what you would actually need to do to build this kind of a thing, but it's going to be, let's just say, a step in the right direction. So without any further ado, let's jump right into it. By the way, all files are available to Patreon supporters. I keep telling you this, and this is important. So if you don't want to model something like this, or if you want, a base and everything to kind of match between what I do and what you see on your screen, just download the files, support the channel, and then download the files from the Excel spreadsheet that's going to be provided for you. With that out of the way, you can just do exactly the same kind of procedure on any type of a sub-D form, so it's not like you need to use this one precisely. And with that being honestly said, we could go a little bit simpler. So for instance, what if I just create a bounding box around this form? And let me just create go to sub-D tools. Let's make a new layer and call it temporary. I'll just call this temp. And within that layer, I'm just going to create a box so that at least at the start of the tutorial, everyone has exactly the same thing on their screens, right? So let's create a sub-D box, create sub-D box, divisions 2 by 2 by 2. Make sure that that's a thing that's happening. And let's just make it like so, delete. We have ourselves a little sub-D box, right? That has these kind of divisions. And then I will just, we can make it a little bit funkier by just Control-Shift, grabbing some edges, pushing them down, grabbing others, pushing them out. Maybe not, maybe just grabbing the edges and using bevel edge or bevel on these, just kind of cut into it. Maybe on this side it's a little bit more aggressive, something like that. And then we can do we do a bevel or an inset? Let's do an inset. Inset, not insert, inset. We just select these faces here and here. Oops. As a group, so mode equals group. And then for the distance, I will just use, let's go for 50 or 100. Let's go for even more. I kind of want the inset to be pretty aggressive, so let's go for 500 millimeters. Something like that. That should be good enough. Then you can just kind of grab these, extrude them inwards. Don't forget the gumball circle enables you to extrude things. Like that. Yeah, that's good enough. So this is gonna be the form. By the way, if you're curious about the size of the form, so that we all have the same size, if I measure the distance of the bounding box, it would be, the length is 26 meters or almost 27. The width is 9 meters and the height 23 meters or 24. So it's like width 26 or length 26, height 24, and width 9. Okay. Back in here, not in here, but back in our little Revit window, we also have this kind of a Soviet building block that's built in Revit, and it's very, very simplistic, nothing fancy at all. So I assume all of you will be able to do the building block, you know, by yourselves. Again, this is also going to be available for Patreon supporters if you are lazy and don't want to do this. Anyway, getting this into Revit is pretty simple. I can just type in subd, right click in Grasshopper, sorry, in Grasshopper. I type in subd, set one subd, like that. We link these. By the way, if you don't know how to open up Grasshopper, first of all, watch the first video of the series. Second of all, the button is right here, the big Grasshopper button. So Rhino.Inside.Revit, run Rhino, run Grasshopper, you're good to go. So with subd linked in Grasshopper, we need to somehow carry it over into Revit, and I will do it in a very kind of quick and dirty way. I'll just convert it into a brep. It automatically converts what was subd at first. Let's make this a bit bigger like that. Let's hide it, and let's hide the subd in Grasshopper. So click the scroll wheel and choose the blindfolded guy to hide things. It creates this kind of a poly surface object that you can see has a bunch of patches of surfaces, and now this poly surface object is able to be inserted into Revit by just, if we go to, let's find Revit tab, under direct shape, you can choose add brep direct shape, like that, connect, wait for it, immediately jumps in. For some reason it's complaining, brep builder cannot assign edge geometry to edge 18. I assume if we just, yeah, sometimes it just works if you disconnect and reconnect the wire. Disconnecting is control, using the holding the control key and dragging backwards. So if you disconnect and reconnect the wire, now it's not complaining. I have no idea what's going on with the exporter, but hey, if it works, it works. And now we have this kind of a mess of a thing here. Some edges are not even visible, and it's all, you know, the shape is pretty accurate and it would render out correctly, but it's not great. And also it has nothing to do with buildability of the thing. Like, this is still just a generic model, I believe. Yes, it's a generic model, right? So not great. Okay, how do we make it great? First of all, we delete it. Then if I show you here, once you delete something in Grasshopper, Revit will start complaining like crazy. So we just choose to delete all, and then it gets rid of the representation of the Grasshopper geometry in Revit. And then we start, well, we start building it up. So the first thing that we want to do is take this brep and create a beam structure. So let's actually just look at the Rhino screen for now, like that. We want to take this brep, and from the edges that we have here, we want to create a network of beams that connect, right? So that's not going to be an easy task because it's going to be so heavy and everything is curvy, right? One way would be to just extract control polygon, subd control polygon, to use this to get the low resolution mesh. Sorry, let me do this real fast, bifocals, like that. So we extract the subd control polygon, and then we use Catmull-Clark subdivision. If you don't have this tool right here, it's Weaverbird plugin that you want to find. Weaverbird. Oops. This plugin. Just Google for it, Weaverbird Grasshopper, you'll find it. And we just simply connect and give it level 2, let's say. and instead of a B-rep we can look at the mesh, and you can see that the mesh has much more, like a much denser network of edges, and all of these edges, every single line here is a straight line, it doesn't curve. So there are two approaches to this. The problem with the straight line approach is just the sheer density of beams that you get. The approach with the B-rep is that your beams are bent, so they are curving, but you don't need to have as much. I think the curving beams are nicer to look at, so we're going to go with the B-rep approach. So to get the edges out, I will just deconstruct B-rep. I'll deconstruct the B-rep to get the faces, edges, vertices. We'll deal with the vertices later, but for now, I care about the edges, right? So with the edges being present in this output right here, I can, first of all, remove all of the crappy ones, all of the edges that are way too small to become a beam. I'm not sure if we have any here, but we're going to definitely have some, well, perhaps an edge like this. Perhaps. No, I don't think there will be any edges that will be removed from this, but it's just good to have that filtering system in place, so we'll do it anyway. So for the edges, let me just create a curve component, just a curve component like so, and connect it. This does absolutely nothing, it just, I don't know, it helps you visually structure what's where and what you're dealing with, right? So since curve is kind of going out from edges and I can see curve component here, I know that I'm dealing with lines and, you know, two-dimensional objects. Okay, so we have curve. How do we filter out the shitty curves, the small curves, the thin curves? We use, we measure their length for sure, curve length, or just length, not list length, by the way. Make sure that you're not using list length. that would be bad. Curve length, like that. And we ask, is the curve length larger than some number? Let's say this is in millimeters, so let's say 250 millimeters, something like that, and connect it. And we get a bunch of answers, yes or no. And if it's yes, it should be kept. If it's no, it should be removed. So we will use cull pattern. Cull pattern does exactly that. It takes a list of curves, and according to the answer that we're getting from this output, yes or no, for each curve, it's going to either keep it or remove it. So we just connect it like that as a pattern. Let's just double check. We had 178 curves, and now we have 178. So this filter right here, let's call it filter, this does absolutely nothing right now. But if you had a messed up geometry that had a lot of small edges, it would deal with it quite well. Now, next thing that we need to do with the curves as they are right now is simplify them. Right now they have way too many control points. Even if you don't see the control points, I know for a fact that each of these curves has way too many control points. Revit is going to scream if you give it too many control points. So we need to use a tool that's called Rebuild Curve. Rebuild Curve. And there's like two tools here. I don't remember which one we should use. Let me just do one little quick test here. Give me a second. Alt Shift click, no, Alt Control click shows you where each tool is. Okay, so one belongs to pufferfish, the other one just is pure Grasshopper. We're going to use the one that doesn't require you to download a plugin. So just Rebuild Curve. We connected our cull pattern output to Rebuild Curve. And it asks us for, okay, what's the curves? So we already gave them the curves. What are the degrees? Degree of, not continuity, the curvature degree. Degree 1 is polyline, degree 2 are arcs, degree 3 is a smooth NURBS curve that cannot be exploded, degree 4, 5, and 6 are mathematical. Like it just keeps adding more and more control points on the handles, don't worry about it. So for this, we will definitely will use degree 3, because we want the curves to be smooth, like perfectly smooth and explodable. But we will decrease the number of points to, let's say we cap them at 5. So 5 points maximum. 5 control points. And you can see that visually, I mean, okay, so between the original, which is right now in green, like that, and the rebuilt, there are gaps, but it's very minuscule. So reducing the amount of control points greatly doesn't mess up the geometry in the same way, right? So the geometry stays quite good. Anyway, now this is where it starts to get tricky, because I want to create, if I were to, let's say, pipe these, also, where the hell did my curves go? There we go. If I wanted to pipe these, I could, you know, I can just do pipe like that and give every curve a radius of 5. Oh, well, that's 5 millimeters. That's stupid. Let's give 75, right? So we get the pipes. But the problem is the connection right here, right? So if you want to have like circular pipes that connect at a certain, you know, single point, you can use the pipe command, and then you just simply, under end caps, you choose flat holes. So you just right click and choose flat on the E input right here. So it's going to cap every pipe, and then you would use in Revit tab, direct shape, add geometry direct shape, like that. You would name it / framing, or you can just type in panel, grab the panel, and then type in framing. That works as well. And then connect it to the name. The geometry is going to be the pipes. Sorry, that's the category. Geometry is the third one. So for the category, we need to go to direct shape categories, and basically here we just choose what kind of Revit category the geometry should be in. So we'll say mullions. I think that's mullions, curtain wall mullions. I think that's the best for this particular application, like that. That's the category, and for geometry we just use the pipes, and we pray that Rhino or Revit is not going to crash. So it's going to slowly go through the 178 or whatever it is pipes. You can see that it's counting, and every single end of the pipe is complaining for some reason. Cannot assign edge, failed to convert geometry, some problematic faces, blah blah blah. There's so much crap. So one thing that I want to do is I want to first of all get all of these guys into one big happy list. I'll right click on the pipe P output right here, and I'll choose to flatten it. What this does, it converts, like, every single piece of geometry is pushed into one list. So technically all of the pipes should export at the same time. This, as you can see, then gives you much less errors. And then let's disconnect and reconnect it again, because sometimes that just helps. Never mind, it's still red. If it's red, it doesn't mean that it's not working. It just means it had to do something to fix the geometry to be able to export it. Rhino.Inside.Revit is still not the most stable of the tools, but it does the trick. All right, so this is what we have with the pipes, and I think that looks pretty good. I mean, the connections are not great. You could use Boolean operations and so on, but you know, they kind of connect. And you get the framing system in place. But what if you don't want circular pipes? What if you want something a little bit more fancy? At that point, you need to start creating rectangles at the ends of each curve and sweeping along the curve with the rectangles. And we're going to do exactly that. So instead of pipe, we're having that's fine, but instead of pipe, we're going to use sweep. Sweep 1. This tool right here. This tool right here requires us to give it a rail, which basically are these curves right here. You know, each of these curves will be a rail. It asks you to give it section curves, not necessarily a single section. It can be 2 sections, and it's just going to create a rail along that. It's going to create a sweep along the rail in between the 2 sections that you gave it. And the third one is the type of a sweep that it's going to use. Default is fine. So first of all, the rails for sweeping, that's going to be our rebuilt curve, rebuilt curves, like that. And one more thing that I'm going to do is I'll right click on the rebuilt curve C output, and I'll choose to graft it so that it's, how do I explain this? 1 second. When it's grafted, every curve is in a separate tree branch, data tree branch, meaning that every single beam is going to be worked on separately by the Grasshopper script. Maybe that's the best explanation or simplest explanation. Okay, so now where do we want the beams to start and end on each of these lines? We don't want them to start or end right at the start and end of the line, because that would be we wouldn't have any gaps to fit in the connectors, you know, because in between the beams you have the connectors, unless you're dealing with the pipes. The pipes don't need those, but for rectangular ones you usually do. So what do we do? First of all, let me 1 second, like that. Okay, we need to evaluate length of the curve, evaluate length, just like that. And we need to say, okay, what's the offset from the end of the curve? What's the offset at which we want to get the start of the beam? Well, let's say 50 millimeters. From each single curve, normalized length. Okay, for each single curve, we want the length to be, you know, 50 millimeters from the start, so 5 centimeters of a gap. Then it's complaining that normalized length cannot be larger than 1. And this is the third input. This is because of the third input, which says that if true, the length factor is normalized to be between 0 and 1, so it's proportion based, meaning 0.5 would be the middle of the curve. We don't want that. We want it to be millimeter based. So I'm just going to create a toggle, Boolean toggle, and choose false here. And now you can see that each curve, let's say like here, this is good. The gap here is 50 millimeters. The gap here is 50 millimeters. Here and here, these 2 gaps are 50 millimeters along the length of the curve. That's perfect for us, because now what we get is we get a parameter on the curve, on each curve, that tells us where that 50 millimeter gap actually is. So we can use those parameters from here to calculate. To make sure that sometimes for some reason it gives us a parameter that's a negative value, which is very weird and shouldn't be happening, but just to make it foolproof, we can use absolute numbers. So absolute, we just connect it like so. All right, and that's all we need to do to be able to create not just a rectangle around this point, but also a rectangle around a point opposite from the curve, because all we need to do to get a point that is on the other side of the curve and also offsetted by 50 millimeters is to just take the parameter value and remove it from 1, because if 1 is the endpoint and you remove whatever this parameter is from 1, you will basically be stepping back by this gap backwards along the curve. So that's going to be a trick that we're going to be using. So let's create two frames, two perp frames, perpendicular frame, two of them. Right click on the C inputs and choose that the inputs are going to be reparameterized for the curves, meaning that we're dealing not with millimeters, but we're dealing with proportion. That's because our the output here as well as here, it's proportion based, not millimeter based, even though here we're evaluating it through millimeters. Then we connect our rebuilt curves to perpendicular frames. We get our parameters here, and initially, like the first parameter is just directly, straight up. We connect the absolute value to the T parameter input right here. But for the second one, as I mentioned before, we will need to subtract from 1. So I'm just writing -1 or //1. You can just have a slider if you want to. And we subtract the absolute value from 1 to get how do you call it, like a plane on the opposite side of the curve. And now it's very messy. Let me just go to display, preview plane size, and let's just reduce this by like a lot. Let's say 100. That should be good. Yeah. And now you can see that it's actually adding the planes. And I don't really understand this. I'm sorry, because since I don't understand this, I can't explain this. But the planes that are created are always double. They're always double in like direction. So how far away they are from the start of the curve. If we are evaluating the length at 50 millimeters, the planes are always going to be created at 100. So whatever number is here, you kind of need to think that if I put in 50 here, the beam is going to actually start at 100. I don't really know why. This seems weird, but it's at least constant, so we can work on it. If someone knows why this is happening, leave a comment. I really want to understand this. Anyway, moving forward, we get a bunch of frames here, a bunch of frames here. We merge them into one list. Merge. Bam, bam. Now it's a bunch of lists of 2 frames in each list. And then we create a rectangle. Let's just create a rectangle on a plane like that. And we need a centered rectangle, right? So our X and Y values will need to be between a negative value and a positive value. So let's say we want a rectangle that is 150 millimeters, right, in length and in width. That would mean that the X should be between -75 and 75, and Y should be between -75 and 75. So that makes the rectangle centered. So let's do it this way. I will just say, and let's do it with a smaller number. Let's just say 70 millimeters, something like that. So how do we make it intuitive? Well, 70 let's divide it by 2 //2. We get 35. Let's get a negative value of 35. So -35 is here, 35 is here. And let's construct a domain. Not squared, just a regular construct domain. Like that. That and that. So now we have from -35 to 35, which makes up a 70 millimeter 70 by 70 millimeter rectangle that's centered perfectly inside of the plane. Okay, so we get our two rectangles here. I believe we can directly use them as our sweeping geometry right here. Section curves. Bam. Perfect. A bunch of rectangles. Congratulations. You have made a bunch of rectangles and swept through them to create beams. So that part is done. Then for the sweep, the output of the sweep, I want all of the beams to be in the same list. So I'm going to flatten all of them like that. And you can see that all of the beams are open. That's because they don't have caps at the ends. So I'm just going to use cap holes component here. Cap holes, just like that. It creates the little rectangles, and then we just connect that to our geometry and put here. Wait for it a bit. It's gonna complain. I believe if we disconnect and reconnect, maybe it's, yeah, it complains less. It still says output geometry has naked edges. It doesn't. Everything here is closed. Don't worry about it. Let's make it also some pretty color. So let's create a color swatch. Color swatch. Let's make them red. Why not? And let's use under Revit material, convert material from red color swatch to a material and connect it there. It will not show up here, but you can damn well be sure that inside of Revit, your rectangular beams are going to be red and very thin. Where's the thickness? Let's do 100 for now. Wait for it to update. 1 second. There we go. A little bit thicker. Still, for an object like this, you would need thicker beams, but you get the idea. Then in terms of the connectors themselves, this needs to be a separate video. There's no way that I can show to you how you can make the connectors. So instead we're going to make something very fast, very fast and dirty. And let's do that actually a little bit later on. Yeah, sorry about that. Let's do that just slightly later on. Okay. So what else? What else? For the surfaces in between the beams. So we have the beams, but I also want the surfaces, like the panels, to be in between the beams. So we need to somehow work with the faces of the deconstruct B-rep. So this output right here. And for that, I basically want to take, let's grab them, surface component. Again, this does absolutely nothing. Surface component. And I kind of want to trim each surface. So to trim away, let's say 100 millimeters, because our division, like we're using 100 millimeters for our beams. We want to trim away 100 millimeters from each side of the surface so that the surfaces fit nicely. So let's try doing that. For this, I will need to use ISO trim for sure. ISO trim, and that's going to be the surface, or these are going to be the surfaces that we trim, and let's work on them separately. Graft it. So we right click on the surface and we graft it. Let's maximize this, and I just find like a nice surface to work on. Let's say this guy right here. So we have it grafted, and then let's go for domain or subset. Okay, so for the domain, if I remember correctly, it uses domain squared. So we need to use construct domain squared. Sorry. Which one? Create a two-dimensional domain from 4 numbers. Create a two-dimensional domain from 2 simple domains. Let's use this one. Create two-dimensional domain from 4 simple domains. This is gonna be easier to understand, like that. And then we need to construct 2 just regular domains. Construct domain, like that. And construct domain. So not squared. And we just kinda plug it in. Let's hide this and let me show you how it works. This is weird. It's acting real weird. So let's say if I specify. Also, wait, do we need to? Oh, I think we need to right click on the surfaces where it says surface. This component, right click on it and choose to reparameterize so that we're working with values between 0 and 1. Reparameterize. Okay, that's good. So you need like these 2 icons to be here. So, okay, 0, let's say 0.3 for the start of both ends and 0.5 or not 0.5, 0.7 for the end of both domains. Trims off, you know, the both sides, and I can, if I'm increasing it, you can kind of see how it works, right? So let's look at the top surface. If I go back to 0, it's going to start touching the initial corner of the surface, and the further out we go, the more it trims from both ends. That's because I'm using the slider for both of these. So we can't just have like, technically I could just do this and call it a day, but the problem is that it's messy. It doesn't look good. So and also like the gaps are not consistent. So we need to have a more elegant approach, and a more elegant approach would be to measure the dimensions of the surfaces, or of this particular surface. We measure the dimensions so we know how big the surface is on both ends, and we need like let's drag all of this a little bit closer to here. So we need to trim off 100 from each surface, but we don't know what that 100 millimeters translates to in terms of proportion, because it changes for each of the surfaces. So to fix that, I will take a number, let's say same number, 100, right? 100. I'll take a number and I will remap it. I'll remap it. So I will say that, okay, we have a number 100, like that, and our source domain, our starting domain, is whatever the value is of this, let's say of this length right here. Let's say 5 meters, 5,000 millimeters, right? So the source domain is between 0 and 5,000 millimeters. And this number needs to be remapped from that particular domain to a domain that's between 0 and 1. So it gets shrunken down into a normalized value. So now I know that 100 millimeters for each surface is of course a different number, but it's basically this proportion on each of the surface along the U direction. I need to do this exact same thing for the V direction. So just in case of U, instead of U, I will use V, like that. And that's honestly it. We have 2 numbers that we can use. Then, how do we trim? Well, we need to start the trim from just using regular values here. My voice is fucking going. Sorry about that. And then for V values, we're using the remapped 100 millimeter value from according to the V dimension of each surface, and you can see that we are getting the gaps that we wanted. And these gaps are going to have a 50 millimeter gap here, simply because we're taking 100 and we're dividing it by 2, meaning that on each side of the edge there's only 50 millimeters. So if I actually decrease this to 50, then the panels start touching the beams. We don't want that. Let's do 60 just to make it clean. All right, we have that. This is good. Then what else do we need to do? Right, the other side. So what goes into B? It's actually the exact same procedure as what we did with the perpendicular frames. Since everything is normalized, the maximum that you can get to is 1, and if you remove whatever 60 millimeter remapped version of 60 millimeter is from 1, you get the offset from the other side. So subtraction, we subtract 1 from 1 rather, this value, we feed that in, and we get our little offset on the opposite side, like that. And we feed again, we do the exact same thing for the V direction or the Y direction, whatever you want to call it, and we get our little offset here. Why is there a gap that is a little bit too big? That's weird. For the sake of the tutorial, I will ignore it. Or actually, wait. No, that's correct. Sorry. No. We ignore these. For the tutorial, we ignore these. This should work on paper. There's no reason why it shouldn't work. Just to be foolproof, we can right click on the S input of isotrim and choose to reparameterize. I don't think it's gonna do anything because we have it reparameterized here, but just, you know, to keep things definitely reparameterized, we can do that. Okay, then we need to make each surface much more simplified. Just like we did here with rebuilt curves for the beams, we need to simplify the surfaces. I will use rebuild surface tool. I really hope that it's, let's just check. No, it's part of Pufferfish plugin, so another plugin that we're going to be using is called Pufferfish. Pufferfish scribble. Like that. It's available on foodforrhino.com, so download that and use that. Okay, so isotrim, we rebuilt the isotrimmed surfaces here. It asks us for what's the point count, and we just use 5 by 5 points, not more than that, in both directions. It asks us for what's the degree of curvature, and actually we can use degree 2 for curving the panels, because they don't really curve that well. I mean, some of them do, but most of them don't curve that much. And you can see that discontinuities start happening if I were to wait, where was it? Yeah, if we were to play around with the panels a bit more, it would fix it, but the gaps are fine to have. We always have gaps in these kind of structures, either way, right? So anyway, we get the rebuilt surface panels, and now it's time to make them thick, to thicken them up. So I will use an offset surface. You could use offset surface loose as well. Let's see if that's gonna work. Wait, let's just check if you need a... You don't need a plugin for that, so let's use offset surface loose, like that. Give it offset the distance of, let's say 2 centimeters, 20 millimeters, like that. Then let's give it retrim. Sure, retrim, keep it the way it is. It just makes sure that if there is a trimmed surface, it stays trimmed. And then we basically, at this point, we just have 2 surfaces on top of each other. I'm just trying to, let's create a thicker gap just for the sake of explaining things, and let me hide the beams so you can see the starting surfaces and the offsetted surfaces right here. I need to loft between them to create, you know, a ribbon around each of the panel. So I will do that by just extracting BREP edges, or you can use wireframe as well, BREP wireframe, to get all of the edges of each of the surface, like that, and like that. You join them up, join, bam. So now each outline is a polyline, basically. Well, it's a complex polyline. We merge these into one big happy family. Well, not one big, multiple, but it's basically we merge them in pairs, and we loft between the pairs of the surfaces, right? So we get these ribbons, and now it's time to merge everything together. So you get the base surface, which is the rebuild right here, and that's the wire. Then you get the lofts that are in between, and you get the offsetted surface right here. There is no way that this is going to merge properly. Let me just check. Yeah, as I hover my mouse, mouse over the output, you can see how messed up the data structure is, you know, like it's all over the place. To fix that, all you need to do is right click on each input and choose to simplify. Simplify. This gets rid of the trash in the address of each data branch, and now everything is clean. There's 3 items in each branch. That's exactly what we want, right? We use brep join, kablamo. Now we have a bunch of joined up panels. We flatten those, and guess what we do? We send them right into Revit. Add geometry, direct shape. We give it a name, panels. Sure, panels. Name. Then we give it a category. Built-in category. I don't remember how it's called. Revit, direct shape categories. There we go. I'll just say, let's say curtain wall panels, or curtain panels, sure. Like that. That's our category, and our geometry is our BREPs, right? Well, before I do that, let me just color swatch. Let's just say that the panels are going to be white, but their alpha is going to be slightly down, so they'll be a little bit transparent. And let's use convert material. Let's convert the material into something that Revit can use, and now we make sure that everything's flattened. That's great. We connect it. Hope that it doesn't crash. Gets red, that's typical at this point. I'm used to it at this point. Just give it a second. Revit takes some time to calculate things, but either way, we are getting the panels that we want, and everything seems to be in order. Oh yeah, and the beams don't follow the curvature of the surface. If you want the beams, well, sometimes they do, but if you want every single beam to follow the curvature of the surface, that is going to be tricky. Let's just leave it at that. And that would require a full course, I guess, to do. But if you disconnect and reconnect, then it's not complaining anymore. So this is a pretty clean export, I think. All right, so we have this done. Let's do the last thing, and then we will actually look at it with the pretty building, because this is, you know, this is whatever. Oh yeah, 2 more things. The nodes, right? The gaps here. For now, since we're not dealing with those, let's create something very, very simple, very, very fast. I'm just going to say Since we already have ViewerBird, let's go for define ViewerBird's dodecahedron, for instance. On each point, we create a dodecahedron with a radius of 100, that's 1000, a radius of 100. And is there like a Revit direct shape, add mesh direct shape? We just kind of add it in like so. Nothing more, nothing less. It's just a dodecahedron on each, you know, on each kind of what the come on guys, come on. Okay, let's not do a dodecahedron because apparently that doesn't work. Icosahedron perhaps. Every time I go off script it doesn't work out, so I'll stay on script from now on. Define icosahedron. This is a bunch of triangles, so we get the deconstruct brep vertices, we create a bunch of triangular meshes. Yeah, now this is not gonna complain. Apparently dodecahedrons, pentagons are not great for Revit. Anyway, we move on. So this is the inner skin. The outer skin, I also want to work on that for just a tiny bit. Let's make it something that's funky. So let's say we have a sub D geometry, and I'll just use the same one for now. Show selected, bam, set one, there we go. So we have our sub D geometry. Let's hide everything in Grasshopper and let's hide everything in Rhino, just so that you can follow along easier. And this time let's extract that. Let's actually extract a mesh from sub D like that, and let's convert or not convert, but let's use a higher density 2. So the higher the density, the more polygons you're gonna have. Please don't play with the slider too much, you're gonna crash your computer. With this done, let's offset the mesh. So let's make it thicker. If I remember correctly, offset mesh is, yeah, it's part of pufferfish, and we already have pufferfish. That's great. Like that. Distance, let's say 200 millimeters, so 20 centimeters away from the original form, so it's gonna be a thicker boy. 200. Both sides, no, so we don't mess with that. But for the create solid, we also want a toggle that says false. We don't want it a solid, we want it to be a single shell thing. Then we will use a very beautiful tool that's called Stripper. Stripper is a Kangaroo 2 tool that comes together with any version of Rhino, that basically takes any shape and it tries to reroute all of the faces so that they form clean strips. Don't worry about it, I guess. If I were to now, after using the stripper, that sounds so weird. If I were to just create a list item just to show you separate strips, so this is one that it created, second, third, fourth, you can kind of see what it's doing, right? It's just getting rows of these polygons. So I have no idea why it didn't use the 6 polygons here, but you know, it's not perfect, but it will do the trick that I want it to do. So we have the stripper. Then I will shuffle around these strips of mesh polygons with jitter, like that. And I will use a list item. Like that. And just simply, let's say series of numbers for the list item. And how many do we have here? 296. So I'll create a slider between 0, ... 296 or 295 actually. 0.295. That creates a slider with the bounds. That's a shortcut to doing so. Connect that to the count, and now as I'm increasing this, you can see that the shape fills up. So in doing so, I'm basically creating a bunch of strips here, and I can say that not all of the strips are placed, right? So it's a little bit of a way of how you can still keep a little bit of kind of control, but also lose a bit of control in the process, but by creating complexity, visual complexity. So with this done, I will offset mesh. So I'll offset each of the strips outwards, and I will offset them. This time they will be solid, so create solid is, we don't touch that. But for the distance, I will use a random number for how many random numbers do I need? Well, that's exactly how many strips we have. So I will say list length, give me basically how many do we have, and I'll use that as my number input here. And then for the range, I will say the range is actually //0 to 3. Come on, //0 to 3. Enter. There we go. So that gives me it's going to either give me 0, 1, 2, or 3, right? And actually I need to do one more thing, and that is right clicking on the random node itself and choosing integer numbers. Once I do that, it's never going to give me like 0.5. It's always going to give me a full number, and I can kind of show it to you here like that, right? And with this being done, now I can create a separate panel where I will specify what are the thicknesses that I want to work with, right? So for every strip, it's going to choose from this library of thicknesses. And since we have either 0, 1, 2, or 3, 4 different possibilities, I will have 4 different thicknesses here. So let's say if it rolls a 0 for a stripe, it's gonna be a thin one, 10 millimeters. If it rolls 1, it's going to be 25 millimeters. If it rolls a 2, it's going to be 50 millimeters. Or 40. Let's go for 40 millimeters. And if it rolls 3, it's going to be 70 millimeters. A thick boy. Something like that. You need to, once you're done, you need to right click and choose multi-line data, or untick multi-line data. Right click, multi-line data, right? So now you have a list, and you can use list item to basically use that as a list, use that as the index, and initially what you're doing is you're replacing your random numbers with these numbers, right? And then you just take these, plug them into the distance, and just watch how every single panel, or not panel, strip, has a different thickness of offset. Neat, huh? I think it's neat. If you don't think it's neat, well, I think it's neat. Okay. After doing this, we will convert this into a B-rep, right? Because it doesn't work as a mesh. We can actually direct shape mesh. Add mesh direct shape. You can actually just investigate how that's gonna look like in Revit without converting it into a B-rep, and just kind of play around with it until you're happy while it's a mesh, because it's so much faster when it's a mesh. So as I'm reducing here, it reduces here, right? You can also have different seeds for jittering. So let's say seed 5. So just different versions of the random jitter, but you get the idea, right? And this is fully connected, but still with different thicknesses. I feel like the thicknesses could be more aggressive, so let's do 100 and 50. Yeah, something like that. You know, so some of these are really sticking out. I think that looks cool. And let's just say the count is just some of them are missing. Yeah, like that. Okay, enough playing around. Let's say you're happy with this, then you continue. Delete all. You continue with just creating the face boundaries. Why is this complaining? Okay, we're back. Face boundaries. So you get all of the polygons around, you get the polylines around each polygon, and you know for a fact that each of them are rectangular, so that's going to be an easy thing to wrap, because we just get discontinuities now. And discontinuities for each polyline gives us 4 corner points, so we can just use list item to just get 1, 2, 3, 4, separate out 4 corner points. Then I can use 4-point surface, and this is where it gets heavy. Bam, 4-point surface. And then for the right now everything's exploded, right? So with this one you need to trust me. You right click and simplify the output to clean up the data tree, and basically you want to merge everything, but not too much, not by too much. Just you want to jump back and merge all of the outermost tree or data tree branches back into the bigger ones, and the bigger ones represent each strip, while the most outer ones represent each surface individually. If you were just to flatten everything, then joining everything into kind of cohesive separate strips would be hell. So instead we will use trim tree like that. This kind of brings us back to 252 branches, which is each branch is a strip, and then inside of them we have like 18 faces, 10 faces, whatever, right? Then we use brep join like that, and that's it. And then we flatten everything like that. The output of brep join gets flattened, and it's a bunch of closed breps, which are the strips. Okay, at this point let's just borrow it. Can I borrow it? Nah, let's create it. Add geometry direct shape. Well, let's give it a name. Outer panels. I keep doing that mistake. Panels, come on, write properly. Then for categories we use I'll just borrow that. Oh no, I hate clicking on the sometimes I just accidentally click on the wrong category, like on the category, and then kind of recalculates. So what are the outer panels? What can they be? They can't be curtain panels. Can I just say generic models? I think that's fine. We'll just use them as generic models as our category. Then for geometry, of course, these come in. They will be transferred. Easy. Since they're flat, it's very easy to calculate. They're in here already. And then back in here, for the material, we can make them blue. Swatch. Color swatch. Let's say some sort of a nice blue tint, you know, something like that, maybe. Yeah, that's a nice color. Swatch. Not swatch, sorry, convert. Like that. Connect that new material. Wait for it to calculate, and we are golden. So now it's done, right? with a very simple shape, we have it already here. Now let's jump back to our original shape, the one, you know, that I actually want to wrap around, because let's face it, the sub-D that we've modeled out in what, 15 seconds, that's probably not the most aesthetic thing, but this one is, at least to me. If you don't think that this is aesthetic, well, it's on you. For me, it's nice. So then I do have two skins on this, the sub-D, the outer, just the outer skin, and the inner structure, and we will do them separately. So let's do the inner one first. So this one, right click, set one sub-D, and just pray. So this will take a little bit of time, and while it's doing it, I'll talk, because I like talking. With the Rhino.Inside.Revit as it is right now, it's still a little bit unstable, and it's very, I can kind of show you. Under performance, if I were to show you, you know, right now it's working real hard, and you can see how much of my CPU is used. So the optimization is not that great, but with that being said, it's, you know, it does the trick in a, you know, as long as you are willing to wait for it to do the trick, it will do the trick, right? And it's going to produce a pretty kind of nice result, I think. So it's not optimized, that's fine. It does break, it doesn't like curved edges and so on, but I stand by me saying that Rhino.Inside.Revit as it is right now is good enough for you to use in an office. In an office setting, it's definitely good enough, it's stable enough to be used and to enhance your workflow, and that is why I'm making these videos, just to kind of test out what's the limit, how far can we go, how does it work with, you know, more curved shapes, how does it work with sub-D, and so on. There will be more, and I'm going to reference this surface as well. There we go. Oh, that was very fast. That was impressively fast. Wait 1 second. Where's our Revit? Yeah, that works. And there's not enough strips, so let's actually get some more in there. I don't really need Rhino for this, I think. Yeah, I don't need Rhino, so I'll just close Rhino, because all I need is just Revit and Grasshopper, which is very weird to do, but we're doing it. So in total there are 804 strips that are made. So I'm going to say for this series, give me like 650 of them, something like that. Now this is going to take a little bit longer. Never mind, it's very fast. So you can really tell that as long as you're 650 is a bit boring. Let's do 500. You can really tell that as long as you're working with flat pieces, it works like a charm. It works really well. Once you kind of move into more curvilinear stuff, then it's chugging along, it's struggling a little bit more. Even with this, it's still giving you the failed to convert geometry error. Let's see if reconnecting it works. Nope, it doesn't. So there are still issues with that, like every single export that we're doing is giving us an error. Still, again, very useful tool. If you want this script, Patreon supporters, available for Patreon supporters. If you want this model, available for Patreon supporters, but I strongly suggest just make your own. Just make your own. Unless you want to support the channel, then please do so. I would really appreciate it. And as we're looking into this, the hell is that? Are we just cutting it in a very awkward angle? At a very awkward angle? I think we are. Yeah, we were just cutting it at a very awkward angle. But this is doing exactly what we wanted to do. The section looks okay. Actually, let us look at the section and let's see if it can deal with the section well. I would argue that this is like good. This is decent in terms of documentation. Of course, if we zoom in too much, I mean, that's not great, but that's because of the transparency in the section. Sorry, transparency of the panels themselves. If I were to remove the transparency, actually, let's do that. View, visibility graphics, curtain panels, no. Apply. Oh, or wait, was that, oops, that was my bad. That needs to be a 0, clear. There we go. You know, once you make it black, it's even better. The geometry is pretty decent. Now I see my stairs are messed up, but that's whatever. So yeah, that is it. That is how you create a structure. Well, a beginning of a structure, a beginning of something that is a little bit more tangible, something that is a little bit more real in Rhino.Inside.Revit. I will leave you with this, and I hope that you will give the software a chance. It's not like I'm sponsored by them or anything. I wish. I really wish. But it's not like I'm sponsored. So just give it a chance. See if you like it. If you do, or if there are any things that you wish that I showed in within this channel about Rhino.Inside.Revit, just leave a comment and I'll consider it. You know, if it's something that I will find interesting as well, I will show it and I will teach you how to do it. Okay, that's it. We're done. I'll see you in the next one. Later.